So today we are going to cover, today's tutorial 8, we are going to cover the last two topics, fairness bias and explainability. Uh, they are quite connected, I would say, like the fairness would tell you what is wrong and explainability can possibly tell you where it's going wrong, like tells you more about the model, the whole idea. Uh, so we'll start and this. Okay. So starting with the fairness and bias part, what type of biases actually do exist? So there are quite a few names to go through, but let's set up a simple structure first. The triangle. Uh, these these are the three actors of a ML model system: the data, algorithm, and the user. Data trains the algorithm predicts, uh, makes the predictions for the user. Algorithm could also, and you can understand it as the model, and user uh, generates the new data with their behavior, how exactly we'll see. And basically the biases do not lie on each of the three nodes, rather it lie on each of the three edges, the three connections to the whole loop. Let's start with the first one, that is the first data algorithm by edge. And here you can say like the whatever the model learns is only as good as how nicely the data was corrected and how it was measured, chosen and measured and used. So starting with there are four biases here that can actually that actually exist between the data algorithm edge, that is data training the algorithm data set used to train the algorithm. First is the measurement bias. It happens when the feature you have selected actually does not do what it intends to do. For example, let's say you have a fitness app. According to your idea, a fitness map should, it would like tell you, classify like, okay, these are the people who are active, these are who are not active, and the features that you have chosen are like the number of steps that a certain person is actually making every day is like it relates to the how active they are. But there are like this is one of the feature that you take, and for example, there are different people who are going to do swimming or cycling or things like that weightlifting, that do not actually register or include like increase the number of steps, but it is a different type of activity which we are missing it because like we are not considering the feature, like what the feature that we are recording does not actually do what they are supposed to do, what they are supposed to measure. The second is the omitted variable bias, basically a relevant factor that you are missing or you are not using. Like, for example, uh, a house price model app. Initially, when it was trained, you did not take into fact the consideration that there is a subway station nearby. So, like the proximity to the subway station or to any mode of transport, like bus stands or something, would also have the effect on the house price. But when you did not collect it as a relevant factor, you did not think about it, and hence now if you are again, even if you are retraining it on the same feature set, it does not improve the bias because that particular feature has been missed and like never been used. So basically, you omitted that.
In the first one, we do use it, but we're saying that it's not
So it's not complete. Like what it's supposed to measure the activity, the total activity, but like for example, for the fitness idea, it is supposed to measure the activity, how much it's doing, but uh, basically it's like the feature is not doing what it's supposed to do. Here we are completely missing the feature. But in the first measurement bias, it's like we are just not reporting that nicely.
number of steps is a feature you're saying, but basically it doesn't count towards the.
No, the number of step is counting towards the goal, but we are missing the heavy like weightlifting, swimming, and cycling type of features.
Aren't they just omitted? We're not including them.
They are So yeah, so the point is that you are not okay, you have the feature, but you are not reporting it properly, or like you are missing the kind of, how do I say that? Uh,
I think it's just
it's
what you want that report.
yeah, like what you are reporting is not the same as what you want to do, but kind of you're missing a
Yeah, wrong scale, for example.
sorry.
A wrong scale maybe. So we have the feature, but we are measuring the wrong scale of it. Or
No, so then that would be the aggregation bias where you are ignoring the subgroup differences, the uniformity of the data.
oh,
So that would go to the aggregation bias here. Uh, it's like, okay, I think I chose a wrong example initially, but like, uh, what I'm trying to say is that the people, so it's like you are reporting, so you are recording a feature, you are using that feature, but it is not actually, providing what it's supposed to. Like, possibly cycling is an activity, swimming is an activity, but it is not actually contributing to the final output, kind of.
it's an extra feature.
Yeah, kind of. Like you are not reporting it. Okay. Let me think of a good example and come back to this possibly, because I think otherwise there would always be a confusion. Moving forward to the third, that is the representation bias. This is basically from who ends up in the samples, like which all processes. Like, for example, the early face recognition systems were quite skewed along the light-skinned uh, people, and darker skinned people unintentionally were somehow not included. And basically, the data set did not somehow have that feature, and the sampling was not proper, the data set usage was not proper. Hence, the representation bias comes in, just because like it's just based on who is included in the sample and who isn't. The fourth is the aggregation bias. This is then one overall model is applied to the entire population, and we are not considering the subgroup differences, the in-group differences, like how we measured before. Like, for example, there is a foot shoe company. It is creating shoes, but like one standard size for everyone, men, women, children. And what it is missing is that the subgroups have its own differences. The width to length ratio would be different for men, for female, for children. It's missing that, and hence it is not working properly, ignoring the subgroup differences. And that is where the aggregation bias comes in. The second edge is the algorithm to user age, basically using the algorithm to predict something for the user. There are five biases here. First is the algorithmic biases. This comes from the choices that you are making during the training process, during the modeling process. Like, for example, your optimizer choice, your what regularization you are using. So two teams who are exactly using the same data set, but same identical data, can somehow still have two different models because of this changes, these differences, and these are the biases that come due to the Bob. Second is a user interaction bias. This is usually an interface limiting uh, what you are using. For example, you have like a job search page where multiple jobs are listed. There are like four pages, 1 to 50, showing total 200 jobs. And for a very weird reason, the website only always shows the first 50 pages. It is not actually going to the next three pages. The user is not able to limit, it's not taking the full potential of the whole data that it has. That is kind of user interaction bias. Users can act on only what is being showed to them, what is being ranked. The popularity bias is when heavily interacted items get often shown, and due to that, the less popular items do not get enough of the stage that they are supposed to. Uh, like it seems similar to each other. User and popularity? User and popularity? And user, yeah. So if there is something like you are manipulating the data, like something bad going on, something adversarial, that would come in the popularity bias. But the user interaction bias is, you can say that it's like how naturally, for example, you have 50 different topics to study from. You have the potential to look at 50 different data points, 50 different analysis, and you as a user are not taking the advantage of the whole thing. So the bias is introduced by you as a user because you are not acting on the full data. Well, popularity bias is not because of just you, the overall population, that a certain thing is, even if it's like it's good, it's not able to come forward. Like you can say Amazon products, some of the sponsor products are always kept above, and due to that, the actual good products that even are less useful are often way below, and you are not able to find them. Kind of that there is something manipulative, like possibly something manipulative going on, but otherwise it's just because of how the interaction is, like the more amount of clicks, more people are going towards it.
The third one introduced by the system. But
Yeah.
the second one
Yeah.
is mostly depends on the.
Yes.
So why this is under the second type of bias?
Because
Algorithm.
because uh, this is what you are getting from the algorithm. Like multiple users together will get it from the algorithm. It's not the issue in the data, the way model was trained. It's not the issue that how users are again behaving towards the new data. It's this happens between the process where algorithm and users interact. Because if you see here, the data is like the data input data to the algorithm is perfect. There was no issue there. The issue came from when the user started interacting with the algorithm. That is why.
Now the assumption is data is good.
Sorry?
Now the assumption is data is good. Now we have the not unbiased, but some.
Yeah, like possibly there was something, but this is created only due to this. The fourth is the emergent bias, that is user population evolves or value shift. Basically, the world is changing after the deployment. It's not a design flaw, but it's like the drift between the model deployment and the actual users of the model. So, for example, the model is trained on one particular cultural context, and now it is put forward to the people with a completely different context, and it has never seen that data, it has never understood that data. Hence, the deployment and the usages appear also sometimes possible due to time, that we are using some old spam filter, but now it has evolved, and hence now the model is not that accurate, like the bias produced due to the time shift. The last is the evaluation bias. Benchmark does not match real deployment conditions. Basically, you have always tested on clean lab photos, but now your model is actually facing the bad lighting, phone camera pictures. So you are not using your algorithm in a correct way. The last is the user to data edge, where the user reacts back into the data. Like, for example, today's user would become tomorrow's data. And there are 4 biases here. Historical data that faithfully reflects an already unfair past. For example, a company's hiring system in the past, it has always seen that for a particular role, more men are usually chosen as compared to women's, and that is in the data. Like there is nothing wrong with the data, that was the pattern, but that pattern is now actually going back into the model for its own like self-learning, and which is creating this bias. Population biases user differ from the intended target population. So something made for US people is now being used for like Indian or Asian kind of people, where the everything changes. For example, a simple face recognition app like the Apple, I think, had that issue initially, that it always trained on US faces, and then it could not work nicely on the Asian faces. So that users are differing. Self-selection bias is that there are some subjects who actually choose to volunteer to use their data in the data set, and this would sometimes skew the sample. For example, Google reviews. Most people who are actually reviewing something, either they are very like not happy about it, or they are very happy about it. The normal neutral reviewers actually never put out a review. Basically, there is always a gap in the whole distribution. Uh, the data ends up being polarized. The last is the social bias. One judgment's shaped by another judgment. For example, a junior researcher asked to review a paper, changes his or her opinion based on how the senior researcher has already reviewed the paper. The bias comes from the behavioral end, from one's judgment to another. And these were like the 13 biases, I think, that are overall there.
I have a question that should we remember all of them? So we should name them in the example and explain them because it's pretty difficult.
Yeah, it's difficult. Usually, what you are given is the first question that is in the question sheet. You are given a certain type of question that this is something that we have. Can you just decide that what bias would it include into? So, for example, you have this hiring model ranks resumes containing phrases woman team. It's not related anything to the data, it's just the model behavior. So it's how the model behaves. Hence, you go into the edge that it has to be the user to data edge, because neither the model is doing anything wrong here. It's just because it is containing certain type of phrases. Hence, it would go into this edge, and hence you choose the correct. Ideally, you're not supposed to remember the definitions of each of this, but you should have like a clear enough idea that this should go into this type of bias, because that is what usually they ask.
So it's not the case that we should name each of them, but it's the case that we should
be able to
likely
classify.
decide, that based on this scenario, on which age.
Yes, sometimes not necessarily that only one type of bias exists. There could be multiple, but you need to have an idea that these are the possible type of biases. And this was actually a question that was asked in the exam. So
we do need to know what the biases are. We do need to know what historical biases, all the five biases within.
You won't be asked to write the definition, but
the type of bias.
yes, you need to classify it. So the ideal way is to first think that where does it lie in this triangle, and then so.
For example, in the questions,
Hmm.
you mentioned that this is a historical. What is it isn't algorithms or algorithms for bias?
Okay, so hiring model downranks. Okay, let's read the whole question first. Downranks resumes containing this. Okay, it's exactly what I wrote. So, when you think of that, like the question states that the hiring model downranks resumes containing the phrase something. So first, the main idea that would go is that is something to it either has something to do with the data, or like you can think of it as you said, that it could be something algorithmic, but you don't have any other data here. Like you don't have any data regarding the model to actually judge that was it an algorithmic bias. It would depend it would depend highly, like much on the sentence, the formation, the words in such type of questions. Because if you're given more information about the model, that it was the model training, that it had like some particular amount of sampling issue or something like that, and due to that it happened, then it would be in that category. But here you don't have anything like that mentioned, and hence you have to work on what you have. The word phrase women's team, and it just that it does not actually, the question does not say that what created it, like what issue came during the training, during the what, etc., to figure out. So the only hint here you have is the phrase women's team, which makes either it is something related to data to model, or it is user to data. It's nothing like you are inferring something from the model, hence not algorithmic bias. Very subjective type of questions, but you need to just know the difference between each of them.
Said that the historical bias and real time mixed with a measure or reporting or measurement bias, because the historical bias could have been potentially cleaned out if the right things were measured and the right things were also excluded, maybe features, but since it's
Yes.
great women's team, probably it's the resume. So this could have maybe been kind of cleaned out of the data, and then this I attributed this to like kind of measurement bias as well.
I would agree to that, but at the same point, in the same place, the question does not mention anything about was the training data measured incorrectly or correctly.
I mean, not like instead of correct or incorrect, but like even if you have some historical bias, you could have, or at least attempted to basically clean your data and mitigate this historical bias. So by consciously deciding to include certain features such as terms relating to a gender in your resume, you basically include some of the feature selection decision, and that's basically what I interpreted as having a measurement or reporting bias, that you basically explicitly decide to report this words in your resume to your trained model.
So I would argue it if for that thinking is that for the reported the measurement bias, you don't like so your model is not like when you are just saying a hiring model, I possibly yes that it was due to a feature that was not measured properly that this issue came up, but at the same time it's again highly specific to the question that the question does not hint towards anything like that. Like the questions possibly that would be asked to you would be like very specific in their way that they either maximum have like one or two of the biases, like that it's kept very specific that you don't actually go and think in that way. I would agree that that would be like the second best bias to add, that it is due to the measurement reporting error that this particular type of data entered the system in the first place. I agree to that, but then the question does not really mention anything about the training data here. Agreed that it is based on training data but when you see the question, it's based on the output of if you see the hiring model downranks resumes, it's on the output that the model outputted something and the bias is there. Like the issue came from what the model outputted.
I just deduced from a question statement that since the model was able to downgrade on a certain term in the resume, this implies that this term was not cleaned out in the training data. So that's basically because otherwise it cannot value on this word. Right?
Like think of that there is a mining position. For example, a company has a mining position. Even historically in the past, everywhere, if you see, there are not a lot of female miners. There are as like more. So if that data is by default given to a model, the first thing it would actually, like it makes sense that it would by default down rank such type of positions for women's. So it is and I don't think there is a way that you can actually mitigate it completely unless. So like this is something that the model by default will learn because that is how it's actually in the life. It's like in the real life, unless you are balancing your data very well, that you are also giving it some mining options that have females, it's going to be difficult. So like the way to actually balance this, what the idea you had would be sampling that we'll be discussing further. But yeah, the second would be the measurement reporting bias. But the idea is to not think of where it originated, but where it's affecting. What it's affecting.
Second thing can be used data to model. Yeah.
Sorry?
What he said can be the second.
Yeah, it can be, yeah. Yes. The second is a churn prediction model degrades in accuracy after a new competitor enters the market despite no changes to the model itself. Again, here One of the thing is omitted variable bias, that the model never took into account that there could be competitors in the same idea. Like if I have to figure out, like if this particular model, a churn prediction model has to figure out this system is better or this system is better, it has to take into account all the competitors as well to rate a particular model, right? And hence, uh, degrading this would mean that a relevant particular factor was not actually included in the factor of using, like checking with different competitors was not actually included in the feature set, hence omitted variable bias. The second that possibly could come would be the emergent bias, that due to the time shift that it happened, that initially the model worked very well, but as time progressed, it did not take, but that is a very far off option there.
When we are retraining, aren't we assuming that we are now including the feature?
So if not mentioned that the feature is now included,
And then
retraining does not mean like you are possibly still retraining on the same feature set,
Okay.
unless and until it's not mentioned that you are retraining with the added feature, it would still be the omitted.
Which is why can't retraining fix it? So we're assuming that it's not added.
It's not added, yes. Retraining on the same feature set does not account. If you are adding the feature, definitely yes.
Possibly correct here.
Yeah. That is what I said, that due to the changes after the deployment, this is possible. But that would also include that there is some time shift, something new, like something new has happened in the world after deployment. But here also the case would be that the competitor is already there, you just forgot to add that feature, use that feature.
The thing it says like the model degrades after a new competitor enters. So this sounds for me like the model was deployed and after this, the new competitor arrived. So the variable couldn't have been measured at training time because there the
But like you have to take into account what actually a churn predictor model does. It is supposed to rate something, and when you are rating something, you are going to compare it with other things. When you're comparing it to other things, you are supposed to take into account the
Even
competitors.
It could also be that the model actually has some feature for accounting for other competitors, but the new competitor was simply not.
Yeah, but like at this point, we are assuming things.
Maybe not reported.
Yeah, at this point, we are assuming things, I guess. Like, if you have a lot of idea, ask the people in the exam what do we actually mean here. The last one, okay, again, the complicated one. I think it answers your.
The first one, it imagine.
Yeah, that is what we were discussing, that possibly yes, but then it's also like the churn prediction model is supposed to do what it's doing, and at that point, it's supposed to actually take in competitor into account.
There are some confusing that it could be multiple.
Yeah, there could be, and most of the time in the questions you are not just asked to name one. You are just asked that name the possible biases that you could think that would work. Sometimes you are asked for a clarification, sometimes you are not. So it will be highly
If we write a merge, we lose marks. That's what I'm assuming.
possibly mean like keep assumptions to the minimum. Strictly fixate on the words, I will say. The third is a search platform shows only its top 10 ranked results per query. Over the time, those top ranked results accumulate far more clicks than lower ranked results. And hence, what would be is user interaction bias, that user are only acting on showing on what they are ranked. Being placed on the top is just causing you to click it more often, and hence you are using it more. It's not popularity bias because the category is specifically about manipulation of some kind, which it isn't here. It's just the way that it only shows top 10 ranked. You're not manipulating anything.
But then there's this overtime. So overtime popularity can increase, resulting popularity.
Yeah, but that is not, you are not manipulating. So for example, I'm giving you like a for example, you have a leaderboard a voting board where you are supposed to vote for different people. Over the time, at one point of time, most people will only be ranking to the top 10 or top 5 teams. Like those are the most popular. There would be very less support for the teams that are not much popular, which makes sense.
That is popularity bias.
No, though, that is the difference. Popularity bias always includes some kind of manipulation, some kind of adversarial. So, for example, bots giving out reviews, some kind of manipulation. That is why I know this would be the question. I mentioned that it is not popularity bias because of this idea that it is specifically about manipulation. You are like an adversary is trying to manipulate this, and the normal user is trying to do something.
Adversarial is manipulation as well. So
Yeah, so that is popularity bias.
so we are not considering manipulation.
No, it's over the time accumulate far more. No adversary. I understand it's confusing, but it's going to be 1 mark question. Don't worry, max 2 marks. Something that you should actually look into is what comes next. Now know that okay, where the bias comes from, but how do you actually measure whether the outcome is fair? Is it biased? It is not. And that is where the 4-group fairness comes in. The questions based on these topics that are provided in the question sheet is the questions that were asked last year, like not exactly the questions, but the same type. The calculation of those metrics is something that you should know. So I would keep an eye out on this. So the first is demographic parity, the simplest one. It says that the probability of the positive outcome should be equal no matter the sensitive. It should be equal across the group no matter what the sensitive attribute is. A is the sensitive attribute, Y is the output. Basically, both the groups or all the groups should have equal approval rate or equal qualification rate. Here, there are certain people based on the income, which in past paid their loan back, some did not. Green and purple paid them back, gray did not. What demographic parity does is that both groups should have equal approval rate. That's it. Basically, if group 1 has 4 people being selected, group 2 also needs to have 4 people selected, irrespective, like 4 people, not 4 people, 4 out of 8. Basically, the rate should be same. 50% here, then 50% here as well. It should be a common equal across all the groups. It does not matter which people are selected. It does not take into account whether the people actually qualify for a loan or they do not. Just the equal approval rate, the most basic one, but easier one to understand and remember. The second comes equal opportunity. So think of like there are two job applicants, both have same skills, same experience, and either one of would succeed if hired, like work well if hired. The only difference here is that between them two is that which group they belong to. And equal opportunity is like going to ask just one simple question that does being equally capable, like having the same features, y equals to 1, irrespective of what attribute, what group you belong to, the output should be equal. So it does not matter if like if you have same skills, if you have everything similar, same, just the sensitive attribute is different, you are still like, it makes sure that both the participants in each group gets equal chances.
The dotted line was 1 point above. It would still hold true, right?
The
right line.
This one?
If it also included this gray, the one that is
This one, right?
it would still approve, right? Or it still hold.
Yes, it would still hold. Basically, what you want to do is that the true positive rate to be equal for the actually qualifying deserving people. So the deserving people are the green and purple ones. So you make sure that the true positive rate is correct. So at least two of the members should be like, for example, if the group one has TPR is as 50%, the group two irrespective should also have 50% for the deserving candidates only. It does not take into account the undeserving candidates, only the deserving ones. So even if like this line was up here, it's still TPRs would still be half and still eligible. It's only among those who qualify, it actually takes into consideration who is trustworthy. Still does not account for who is not, like it does not penalize anyone if they are not trustworthy, but if you are trustworthy, there has to be an equality between you. And this is what the issue is also, that it's not taking into consideration that how many undeserving candidates are being actually given loan or getting hired, because most of the times these are sensitive things. You need to make sure that your false positive rate is under control in healthcare, for example, or loan bank. Even if bank is making sure that one of them is getting, it's highly risking three participants. And just a break, but since I have explained it, I'll come to equalized odds. That is what equalized odds does. It takes into account both true positive rate and false positive rates for both of the sample, for both of the, like all of the groups, not both. Basically, making sure that the qualified people are also at the same rate and the unqualified people are also at the same rate, just to penalize. Yeah.
1/3 there.
False positive rate.
We have 3 dots. Word there.
Wait a minute. Makes both correct at the same rate. False positive rate is 2 out of 4 is the false part, correct. Only one is getting misidentified, right?
Yeah, but we have.
So 1 out of 4. False positive.
Doesn't it only include the gray dots, which are 3 at the bottom?
Yeah, so the 1.
Over 3 gray
Now-
dots.
No, 1 of total, right? It is FP upon FP plus TN. I think, yeah, like it's always wrong upon total. So it is 1 upon 1 plus 3. So 1 upon 4. Bottom is always the total. And like, okay. So basically you want the true positive and
Then over
false.
there it will be 1/3, 2/6.
How many mistakes?
2/6 is 1/3.
2, 3, 4, 5, 6.
So
That is 2 over 1, 2, 3, 4, 5, 6. 2 over 6.
1/3.
That is wrong, sorry. I'll add a circle. Really? Okay. For now, let me just draw. Can we annotate? You need to make it 1/4. So just, I'm going to, how do you clear
And
it?
that will change the TPR but yeah.
No, it won't change it. How do you? Never mind. 1/4, that is, I need 2/8, so 4. So 5. There would be more gray dots. There would be, how many more gray dots? Sorry, wrong slide.
2 more.
2 more. Total 6. Yeah, there would be 2 more gray dots here. I'll add it before adding it, but yeah. So basically the true positive rate 2 upon 4, that is half. Similarly here 1 upon 2, that is half. Here the true positive is 1 upon 4, which is correct, but there I have missed 2 gray dots. Basically, the true positive rate and false positive rates for both of the groups or all of the groups have to be equal. That is equalized odds. It is making same number of incorrect and the correct decisions it's doing it at the same rate. Just make sure that the TPRs have to be same across group. TPR and FPR does not have to be like, so like the TPR, both TPR and FPR for one group does not have to be same. Just a clarity. I did that mistake last time.
But TPR to TPR should be same.
Yes.
TPR to-
Yes. Okay, I'll go with the final one as well, which is the overall accuracy and treatment equality. What it tries is to bring everything together. Here it looks at accuracy and treatment equality, basically a ratio of false negative and false positive. Only accuracy does not work well. We know that it does not work when class is imbalanced. You are not actually penalizing. It does not give you the correct idea. So there is also a similar type of balance for different error rates, which is false negative divided by false positives. What exactly it is? First, you count the so here you take into account for both or all the groups that are present. The accuracy should be same group to group, and this particular error ratio Fn by Fp has to be same over all the groups. Starting with accuracy, accuracy is number of correct upon total number of correct. So these two greens are correctly placed. These three grays are also correctly placed. Hence 5. There are total 8 dots, 5 out of 8. That gives 0.625. Similarly here, 2 are correct here, 3 are correct here, 5 out of 8, 0.625. The accuracy over both the groups is same. Second is a false negative divided by false positive. We have 2 false negatives here in the first, and we have 1 false positive here. Hence 2 by 1. Similarly here, we have 1 false positive and 2 false negatives. So 2 by 1. Going to the questions, sorry.
I mean, understand treatment.
Equality.
Equality, yeah, but what does it mean?
So basically, when you are just using accuracy, you are not taking into account class balance. That is why we shifted to the TPR, FPR, right? So instead of calculating true positive rate and false positive rate all over, we are just directly calculating Fn by Fp, which overall tells the error rates ratio, like how wrong you are. False negative basically tells you how wrong you are viewer. False positive just tells you how incorrect you are here. Essentially doing the same thing, just an easier formula.
Error per class.
You can say that. Going back to the questions, just again a brisk reminder. Equal approval rate is demographic parity. Equal approval rate among deserving candidates is equal opportunity. Equalized odds is equal rate for both negative and like the incorrect and the correct decisions. And treatment accuracy is kind of a mix of the best one, you can say. The first question is why demographic parity and equal opportunity cannot exist together by default. Like it has to be specifically constructed. It's like the two can only coincide by some type of coincidence, not by construction. Exactly how? For example, let's say that there are 10 candidates. 5 out of them, the 5 yellow ones, are worthy in group A. There is group B, where there are 10 candidates, only 2 out of them are worthy. You as a hiring model needs to select 3 candidates. So ideally you want to select the 3 deserving candidates always. So here if you are going to directly just calculate true positive rate, the true positive rate would be you are choosing the best 3, so 3 over 5 total, hence 60%. Here, when you are going to have to choose 3 candidates, you don't actually have 3 deserving candidates, you only have 2. Hence, you are going to have to select one of them which one of them is undeserving. When you are just going to calculate true positive rate, it's going to select both of this in the actual. So it's going to be 2 on 2, that would be 100%. I understand that this is just true positive rate and you don't actually understand why is this the case, but think of it as I want to make sure that demographic parity is satisfied. I want to make sure equal opportunity is satisfied. When I'm trying to make sure that the demographic parity is satisfied, that is equal number of approval rates, that is 3 in both the situation, you can see that the true positive rate, which is basically equal opportunity, is not correct. You are not getting that. Getting this ideally same would be a very coincidence. I don't think you ideally, mathematically, arithmetically, it is not possible to get these two correct unless there is some coincidence that you only want to choose unless the two groups are exactly like the same.
The demographic one looks for the TPR or is it?
Demographic looks for equal number of approval rates. Basically, I want to choose only 3. Like if I even let's say if I choose 1, I want to choose 1 from both group because demographic parity says that I'm supposed to have equal approval rates of each group irrespective of whatever you have. So you are supposed to choose 1 from this group, 1 from that group. Let's say that way. When you try to go to equal opportunity, which looks only for deserving candidates, the number of deserving candidates would be 1 out of 5. Here it would be 1 out of 2. 1 out of 5 is 20%. 1 out of 2 is 50%. 2 cannot match. Arithmetically not possible.
In TPR, the denominator includes both sides, so it shouldn't be 1 over 1 plus 5 like we did last time.
Sorry?
And it also includes the numerator term, the T for TPR.
Yeah, we are including it, right?
We're saying 1 over 5, but shouldn't that be 1 over 6?
No. 1 over...
Why do you think they approved it?
See, let's see. Let's go back to the same question. Okay, this was the idea. For the true positive rate, you have total 4 true.
2 over 4, yes.
Total 4. That is the total number. How many you are selecting? That is 2. That is the numerator. When you go to the example, I have total 5. I'm choosing 1 over 5. So basically, the main idea is 2 cannot be created via construction. If the 2 data sets are completely same, that is possible. Otherwise, it's arithmetically not possible. The data set has to be same. The 2 groups have to be exactly have the.
This question, I think I could always okay when they're well satisfied, but only if I hire only non-qualified people because then TPR is 0.
Yeah, but equal opportunity says only qualified people. It says only the people who qualify.
It's 0%.
Okay.
I think you can always calculate, but that's not a useful case because then you would only hire non-qualified people.
You can go ahead.
These are just selecting 2 out of 2 in that case, basically.
Depends on the demographic parity. How many do you want to? Let's take an example. How many do you want to choose? You can't do 3, so you have to choose 1 incorrect. So let's
like the PR. Right?
No, you are not. Okay, think of it as I'm selecting these 3 because I have to select 3. These 2 will be selected by default, and 1 will come just because of the threshold line. Okay. Now think of it as what would be the true positive rate if these 3 are above threshold and these are below threshold.
Over 3.
There are only 2 positives. It has to be 2 over 2, right? True positive is only colored ones, not colored. The 2 over 2, that would be 100. The third does not count. The third would be counted in false positive rate, but that was not equal opportunity. That would be equalized odds. There are 4 different. Got it? Okay. The question that actually comes in the exam.
better to visualize it this way and then
Yeah, exam questions gives you these graphs. So think of it as you are given this two graph and you are just asked, does demographic parity satisfies? Try. Do you think it satisfies?
Yeah, they're equal above the line 4 and 4. So they have to be equal.
It's not equal.
I
The
mean,
rate has to be equal. So like 4 on it, 50% exactly. Like that could be 8 and there could be 16 and still 4 above the threshold. That would not be demographic parity.
so it also includes
It's the rate. It's the rate. Equal approval rate, not equal approval people. It's the rate.
I thought we were only looking at the stuff that is above the line, but
it
okay,
was-
the rate.
See, it's always 4 by 8.
Hmm.
It's never 4. It's 4 by 8.
Yep.
For TPR, you always look from the colored guys, how many are
Above the line.
And with FPR, you always
Yeah.
look from the non-colored guys.
He's asking about demographic parity. Demographic parity, just
I'm just saying
Yeah.
general for TPR and FPR,
Yes.
because then you can derive.
Yes.
And opportunity.
So if it's 8 and 16 on the right hand side, the rate would still be the same and it's correct.
Yes. Do you get it? Like any questions here? Okay, so this satisfies demographic parity. 4 out of 8, both side. Where should the line go? You have, this is equalized. So from the question, it should be pretty clear that you are only given TPR, so it has to be equal opportunity.
1 point above and 1 below. So anywhere.
So like 1 purple should be above, 1 purple should be below. Everyone agrees?
And one gray should be.
No, it's only equalized opportunity, only true positive rate. Does not care about any of the undeserving candidates.
That's equalized odds.
That's equalized odds.
But even if we do like there.
Yeah, if you draw a line here or here, it won't matter. It won't matter. That is the issue with equalized odds, that it does not take into account the people who are not supposed to be qualified. And yes, your answer is correct. The line comes somewhere between, like 1 purple should be above the line. Must clear the threshold. Well, I would say you scored at least like 3 marks in fairness. This was the actual question that was asked. Going back, does equalized odds satisfy? You have like answer says yes.
I was just looking at it now, but
Yeah. You have to just make sure that the true positive rate for both are equal and false positive rates for both are equal. So 2 upon 4, that is half. 1 upon 2, that is half. 3 upon false positive rate is 1 upon 4, 1 upon 4. Okay. The last one, compute accuracy and the ratio for both F and FP. So accuracy would be how many are correctly placed. 2 are correctly placed here, 3 are correctly placed here, so 5 on 8. Similarly, 4 are correctly placed here, and 1, 2, 3, 4, 5, 6 are correctly placed here. So 4 plus 6 is 16. Okay, so 4 on 16 is correctly like 1 by 4 half. Yeah, 8 on 16. So 1, 2, 3, 4, 5, 6, 8 on 16. I hope it is correct. Wait, no, yeah, wait, yeah. I should really put the dots correctly.
4, 8, and 6.
1. I tried to set Fn by Fp correctly and I messed up the accuracy. Mistakes are not supposed to do in the exam. So, wait. Okay, let's actually calculate the actual accuracy. It is 4, 5, 6, 7, 8, 9, 10. So 10 upon 16 is the accuracy here. that is 0.625. Oh, it's correct actually.
Yeah.
It's correct. And Fn upon Fp, false negatives is, how many false negatives do we have? 1, 2, 3, 4. How many false positives do we have? 2. 4 by 2, that is 1. Similarly here, how many false negatives do we have? We have 2. 1 false positive, 2 by 1. That means I have not done the mistake. So accuracy parity satisfied, treatment equality fulfilled. And here we come to the end of the actual interesting part of the tutorial. Now it's going to be the algorithms, kind of boring. Now we have learned what are the biases, how to possibly figure out whether it is biased or not from the outcomes. So where are you actually supposed to make sure that these biases do not come into the account, and where do you solve it? Where do you intervene with fairness? Again, as usual, in the whole ML pipeline, there are 3 places: before the training, pre-processing, after the training, post-processing, and during the training in processing. First is pre-processing, fixing the data. Basically, you are just going to make sure that your data itself is well balanced, that it does not cause any biases. The first way to do this is blinding. What blinding actually does is it's going to make the model training immune to sensitive attribute. Basically, either you are going to omit a whole feature, a sensitive attribute like that. That is called soft blinding, where you are omitting one particular feature, one sensitive attribute itself before the data gets trained, before the data is used for training, so that the bias does not occur. One issue with that is that it is sometimes weak to proxies. So for example, if the main sensitive attribute is the country I'm residing or the city I'm residing, I'm removing that city, but I'm still keeping the pin code, zip code, a proxy to that thing. So soft blinding is an issue there, that it is still not immune to the proxies. Hence, there is something called as, what is it called? It is called zip. They're alone self-sufficient, and the stronger version is true blinding. Basically, what you are going to do is you are going to find the correlations between the features and remove all the correlated features. Not actually possible, because something like basically you are going to make sure that you are removing the proxies also by different methods, which is not always that possible, because some things are by default correlated due to XYZ reasons, and removing that decorrelation feature would also remove the actual important feature, important data that you actually require for model performance. Hence, blinding is not always the best. It depends on the data set you are using, that whether how much data you lose makes sense or not. Second is sampling. Basically what I guess you were discussing there, that you make sure your data set is well aligned, that issue of the demographic equality parity does not come, that you are just making sure that you are sampling it properly. There are 2 ways of sampling the data. So for example, here you can see the blue dots are much more overrepresented as compared to the yellow one. So it makes sense if the model is more towards the blue one and not towards the yellow one. So what you want to, there are 2 options: you either downsample or you upsample. Downsampling is you are going to remove the overrepresented class. The issue here is that you are losing the variation, the different category of data. You are losing good information here. The other is upsampling, basically you are deduplicating the underrepresented class. But here the issue is that if, like for example, if half of the data is just duplicated, the model is more likely to memorize them leading to some other issues.
Blinding always requires omitting features, right?
Sorry, blinding?
Blinding, we always omit features in processing. One way or the other. Can you say this part about memorization, that it's memorizing?
So, for example, I'm upsampling something. So, this is the underrepresented class, this is the overrepresented class. To handle the sampling, what I can do is I can just duplicate this data to make sure that both are equally represented. But since it is duplicating, the half of the samples here are the same. The model is saying same sample multiple times, hence could create memorization, privacy, data, etc. So the second is pre-processing, fixing the, okay, no, it did not change. In processing, fixing the training itself. Again, two ways to make sure that there are less biases and building fairness is one, you are either reweighting or you are regularizing. Reweighting is basically instead of deduplicating the samples or something, you are giving every sample, every single individual input data, a particular amount of weight on how important that particular data point is for the model. If it is more important, give it more weight, this WI. If it is small, it is not very important, you can give it like a normal weight. So in the question here, when there is like underrepresented data, what you could do is simply just give that a higher weight so that the model learns its importance over the samples that are readily available for the model. Second is regularization. We all know what regularization is. ML, you are adding a fairness penalty. Fairness becomes the part of what's being optimized. In reweighting, the loss function structure is not changing. You are still using the same loss structure function. Here you are actually adding a fair penalty based on the lambda. Third is post-processing, fixing the output after the model is already, we are trying to make the model fair after the model has been trained and is ready. Thresholding, that is what you learned for the four-group fairness. You are going to change the boundary as per your requirements. Change boundary for the groups, the four demographic parity and etc. Everything lies here. The last one is calibration. Basically, you still have a common threshold. For example, the raw score of 0.7, but now it means something else other than 70% for a particular team or a group. For example, for a group A or for a particular feature, 7.7 threshold would still remain 70, but considering B is overrepresented or something, we just make sure that the 0.7 is calibrated as 55%, a little lesser as compared to 7, basically calibrating the raw score, fixing what the score means, not changing the boundary. The boundary is still 0.7, remains the same. That ends the fairness part. Any issues, any questions?
Say that the regularization is more flexible or automatable than the reweighting. Then imagine that in order to choose the weights, you kind of have to know what you want to upweight or down.
Yes, yes.
Could also
Yes.
Make the weights parametric in terms of
Yeah.
other features, but
Yes, finding weights per input is going to be difficult. Yes, like for you have 50,000 data samples, you cannot sit and weight every single one of them. It's tedious.
Generalization would be better to get both in the model.
Yes, it's directly affecting something. Like it's directly affecting the model here. It's also affecting the model, but there's a lot of manual work involved. Like even if you just start with that, these are the outliers that I need, and other than else, you just weight everything equal. That also works, but again, there is a certain manual work or regularization is easier and well tested. Okay, so going to explainability. So explainability is basically understanding what is actually happening inside these models, not just whether the outcomes are fair or not. For example, there is an input to a model, there are model weights, activations, etc. There is an output and you look at the output. For example, you have an X-ray of a lung and figure out whether the person has pneumonia or not. you have like all the weights, all the activations, none of them are hidden, none of them are encrypted, but still mapping the grade, mapping the weight, the activations, or that particular neuron to a particular concept is not very direct. You cannot directly map that this neuron fires for this particular feature or this layer. You can have an idea, but you don't exactly know. You cannot explain the model, the weights, everything. It's not hidden or encrypted, but just out of our understanding. And this also has legal consequences that GDPR Article 22 has gives people the right to contest if your decision was made solely by automation or it has some significant effect on your life, like loan approval, hiring, etc. So understanding what you are outputting, what the model is learning is much better than, in normal words, vibe coding is not that efficient as compared to actually knowing what the code is doing. Similar idea. But this is about the model, not about the code. We have some idea that what a CNN learns layer by layers. Initial layers have basic boundary, text, edges, color gradients, where it changes. When you go deeper into the model, it starts to figure out it learns some textures like repeating patterns. At even later, the later layers are usually for parts, wheels, whole objects, and all. And the final actually figures out what concept it is. It is a cat, it is a dog, is it pneumonia, is it car, etc. based on them, what you have. Because this feature are emerging automatically, you never told the model that the first four layers are only for edges or the second last four layers are only for objects. You never manually hand designed it. It's the model that learns it that way. So there is no need of manual feature engineering, but which also makes that you do not understand which layer is doing what, and that is why explainability is important. You should know what, like, you should have different interpretability tools to understand what a layer represents. And before going on, a lot of times there are, like, over the lectures in different papers, units are mentioned, and it is always good to know what these units mean, especially for explainability. So first, for a CNN, let's say, there is like the whole explainability topic here is based on CNNs. So the first we start with a normal filter. A filter is not a unit, but you know what a filter does. It's going to convolute, multiply it with the image position, multiply it, get the activation, etc. That is a tool for explainability, but not explainability. And that is what the single neuron your convolutional means. Basically, you are putting a filter around this as this being the center, calculating the activation, and then that particular activation here is a single neuron convolution, which could be called as a unit. Second thing, what a unit is called is that if I'm just running the convolution, instead of just at one neuron, I'm going to run it for the whole image for a particular on the whole image once. That would be a channel. That could also be a unit. If I'm considering multiple channels into account, basically a whole layer has multiple channels. So one image, one filter will give you one channel. That way, if a layer has multiple filters, it will have multiple channels, and that could also be considered as a unit. So it is very important to make sure that you know which unit you are working about, which unit you want to explain, whether it's a single neuron or it's the whole layer. And similarly, a single neuron, these are the convolutional part. This would be the normal fully connected layers part, where all the one particular neuron has the output from all the previous layer neurons. So that could itself, in a fully connected layer, that could be a unit, or the whole layer could be a unit. And just to give again a clear idea of what an activation or an activation grid is, this is your input image patch. This is the filter or the kernel. This is particularly the vertical edge filter. you are going to multiply and sum, add the bias, possibly apply ReLU and get the activation. This is an activation cell, it is an activation for this particular patch. If this is the whole image, you are going to convolve your filter at different positions and hence get different, like one activation for one particular part, second for the next step, and hence you get the whole activation grid, one cell for the filter position. The same weights are applied everywhere, so shared convolution, the basic CNN ideas. Going back to the actual explainability foundations, there are two types of explainability methods. One is interpreting internal units. The second is input attribution. Interpret internal units is basically what does a particular neuron or a channel or what does a particular unit means. Input attribution is which part of the input drove this particular prediction. This is for the model, this is for your input. There are two separate methods that in the units that we saw, the 5 units possibly, that apply here. And here, there's no units, the unit is your input. For today, since this is like quite simple and direct, we are going to skip this part and just focus on this part as it's usually focused in the exam. That does not mean you should not know this.
We haven't really focused a lot on it's just mentioned in the book.
Yeah, because these, okay, for a basic CNN, you can still figure it out. Like for an LLM, no, it's no one, it's still an ongoing research to actually understand every neuron and what the whole process is in LLM. So by default, this is very difficult and hence not much discussed. Have an idea about these? These are like the simple questions that could be possibly asked, but not usually focused that much as compared to Lime and GradCam. Okay, before what the whole Lime is, and sorry for the ultra colorful graphs. Why do we need Lime? Like what does Lime do and why it is needed? So let's say you want to understand that which part of image is driving a prediction. You have an input, but there is no way you can directly explain something directly from the input, and such a complicated model, you cannot know what the model learns at what point because the model boundary is so complex. So what Lime does is that instead of using the entire boundary and trying to understand the whole model at once, the whole model boundary decisions at once, what it does is it's going to only focus on a very small local part. So it is something like when you see a whole boundary as such, you are going to see that the whole boundary is very complex and you cannot directly understand anything from this particular boundary. But when I'm going to zoom into something in this particular case, this particular zoomed in version becomes like a linear model. So instead of going global, Lime tries to interpret things locally. That is what L in Lime stands for. What it exactly does, once again, keep the idea in mind that it is an input attribution method. Basically, it is trying to figure out what part of the input caused this prediction. So this is the whole image. The different colors you are seeing are like the different objects. You can think of the image like yellow being the sky, this being some flower, this being the grass kind of idea. I think in the question that it is about wolf. So think of this as a wolf and the yellow thing as a sky. What Lime does for the first step, it is going to find out, segment the image into superpixels. Basically, not single raw pixel is not very human perceptible to the person. Like there is a value of 254, what will I do of that? So instead of taking raw pixels, it's going to take a group of pixels that contribute to some part of image called superpixels, and it usually does it with this algorithm Slick. It is model agnostic. It has not seen the actual model or anything. It's just the part of the image, like a pre-processing that you do on the image. what happens exactly is, in the second part, you take this image and you randomly mask certain parts of the image. I like for the first, I just mask the wolf. Second, I'm just masking the sky. Basically, the model is not able to see what exact uh, pixels were there, what exact idea was there. Then it takes the model that we are supposed to explain. It's a complete black box model. LAM does not care what the model is. It uses it like a black box model. It's going to take these images and query the model. The model will give you some raw logic, some prediction values, some classify, some labels. What it does is it takes those logics and instead of going global, it will train a small linear model, single line, single layer model, a small linear model that can be easily understood, and trains the model to understand the boundary between these. So uh, the model can now classify that this type of image corresponds to this feature, this idea. That is, for example, this image is mostly about sky and a grass. So hence probability. So if you intuitively think it is being queried by the black box model, we want to understand. If we are not providing with the wolf, like the wolf is masked here, if it is only seeing the image as a sky and a green part, grass, and it is giving such a high probability, you can understand that model is actually seeing what it has learned. It's not focusing on the wolf at all. It does not really care about the wolf. Whatever it is classifying is based on this idea rather than the wolf. Similarly, here, when you see the skies and sky is not there, the probability becomes too low, irrespective, even if the wolf is there. So you're basically we are able to find out that out of the whole image, what part of the image the model has actually understood and learned to classify. Like ideally, if it is a classifier model, usually it is for this particular, it is supposed to classify wolf, that it is a wolf. But what it is learning to classify that it is a wolf. Here it is, you can see from all the three, the first one has the highest. Basically, it's focusing more on the sky rather than the wolf. And hence, this linear surrogate model that is being trained here outputs the coefficients for the first image, the first mask much higher. And you can see that instead of the sky region overall, using this, I'll explain what this is. It's able to rather find out that it's making sure that the image is classified as wolf, but what it is learning is the sky, not the wolf. Basically, it shows that the model is mapping the sky to the wolf rather than the actual wolf to the wolf, like the explainability of the model somewhere shows up here. What exactly this is so the linear model that is chosen here to actually classify, like classify the boundary, the actual boundary, the linear model that you can directly understood that is used is the G here. You have multiple different models you can use to actually make sure that the classification is correct and the closest. F is the black box model. G is the all the possible models that you can use to the linear models that you can fit to the local to understand. Pi of X is the proximity, I think also called as fidelity. That is, it makes sure that F is the G's boundaries, the G's decisions are not very far from F. The G's boundary still looks like what F would have around that particular point. And this sigma G is like again a penalty term which makes sure that G is as simpler and as closer to the G is as simple to understand. It's not a very, again, not, it's linear and not again a whole complicated model, so that it's easily explainable, and hence it figures out that which part of the image is actually contributing towards the final output. This is not global, it is rather local. Around it is always this runs always around one particular input data point.
The whole process here is model agnostic.
Yeah, it is model agnostic, yes.
And here we do not segment the images. We just have random masking, right?
So I think Slick is not like it's not completely random masking. The superpixels are basically different objects. So it's kind of segmenting. It's not very close segmenting, like possibly not the whole wolf would be there, but wolf's eye or wolf's tail, like different textures rather than random masking. Sorry, anyone has? Yeah.
So I have a question, I understand this on a high level, but I have a question how this surrogate model, what exactly it takes and what it predicts. So I think it predicts the logics of a specific class like wolf, right?
So
So line is both input specific for one input image, but also class specific for one specific output class, trying to attribute the effect, right? Not for the output distribution in general, right?
yes, so what exactly happens here is that now I have an image. I have a true data that are these coefficients. I'm going to fit a model to this data.
The model gets only the binary information of this segment is active or non-active, or does it get the full?
It gets this whole
masked image?
whole masked
It
image.
gets the vector, not the.
So basically it gets the same input as the original model.
Yeah,
It gets the vector and the black box gets the whole image.
yeah. So this is masked vector. It gets this whole masked, like not, it does not get this original image, it gets the masked
Yeah,
one.
sure, that's true. But it theoretically, you could have also done it in a way that you just say you give it the IDs of the non-masked segments, and then it just works on the binary IDs active or masked basically. But so it has the same signature if like as the original basically.
I'm so I don't get the
So
non-masked.
my question was basically, does the surrogate model get the masked images, or does it just get the binary features if the certain segment is there or if it has been masked?
It gets a vector, like
It
the
gets the
vector that is like what particular superpixel is active and what is not active. It directly takes this image, uses the vector as an input.
So basically the input and output shape is the same as.
Yes, it is the same. Yes.
Also, so the gadgets and we compare the gadgets between
Yes.
S and G.
Yes. And that was line. I don't remember what question was asked on this topic. So I have just included the theory, like the whole algorithm. The second one is CAM. What CAM does is how Lime makes sure that it's finding a particular thing for one particular input locally. CAM does it globally. What it does is that for a particular label, for example, a toothbrush, like some woman is toothbrushing, what it will tell is that what part of the image is contributing to that label. Similar to Lime, but Lime was working locally. This works on the entire model, not black box.
I have a question here. So yeah, I mean, in this lecture it says that we're going to do backprop, but that's during explainability. But during training we do backprop, right? Where we are going to do backpropagation to calculate W's in the first place.
CAM you do not do backprop.
During
Grad CAM you
explanation.
do.
But during training we still do backprop.
The normal backprop, yes, but for this particular, you don't need to externally retrain something. So no backprop there.
During explainability, but like we freeze the weights when we're explaining it. So
Yes.
in that way we don't do
Yes.
backprop.
Yes, but training the model will always require
Will always
backpropagation.
require,
Yes.
even for CAM.
No extra backprop, you can say. No retraining. So, okay, let me start with the whole idea. So, grad chem is think about a doctor having an X-ray again. It wants to figure out which part of the lung is infected with pneumonia. It has two options, pneumonia or no, not a pneumonia. The two labels you can say. And he wants to make sure that the model chooses the correct things, and hence he wants the model to be explainable that this particular part of the lung is actually the reason for pneumonia being occurring. So what it does, it's going to actually superimpose a heat map over that particular part of the image where which is contributing to the particular output, and hence it is called class activation maps something. And what it does is CAM is going to produce a heat map over the image showing which region are relied for the prediction. To get there is a particular architecture requirement that CAM needs. What CAM needs is this global average pooling layer. I'll explain what it is, but this is a global average pooling right after the convolution layers, and between, like, okay, how the CNN works is it has convolution layers, it has like multiple final or one final fully connected layer and the final output. What CAM requires is that between the fully connected layers and the convolution layer, there has to be a global average pooling layer. Why it is needed is because it needs these particular weights, and how these weights are calculated is what we will see here. So this happens during training, like you need to get these weights during training, you cannot get it after training, long before the heat map was actually built. So, okay. So the last convolutional layer will give you certain channels for every image input. The last layer has multiple filters. Multiple filters will have multiple channels. Here we are considering 3 channels. What gap actually does is it's going to take these channels. You can see the highlighted parts are where like the higher values which are actually correspond to the filter. For example, possibly an edge. This would possibly an edge. So the edge filter is uh, fired here. So the higher ones are the higher activation values. For each of the channel, you average all the cells, all the values. Here it is 4 cross 4, so 16 cells. You are going to average the 16 cells to get one output, that is F1. Similarly, channel 2, you get F2. Channel 3, you average, you get F3. That is what this formula is doing. That is gap pooling.
In order to get weights during training, do we use gap in training as well?
Gap has to be in the model during training. You need to get these channels, right? So this has to be done during training. You have F1, F2, F3. These are the 3 outputs that you get after the gap pooling layer before the final single fully connected layer that you have. You apply this 3 or all the values that you have, the gap layer values you have, to a particular single layer, the final layer, and use those weights as, okay. So usually, for example, when you have multiple labels, the final is like a multi-label classification. Here, for example, let's say we have 2. So there is a pneumonia and a not pneumonia. What the gap layer is usually connected is directly, since it is a fully connected layer, it will be connected, this F1 will be connected to this pneumonia output, and F1 will also be connected to the non-pneumonia output. And those are the weights that we are calculating. The weights are class-wise weights, that for pneumonia, this weight would be different since it's a fully connected layer. The weights for non-pneumonia would be different. That is, again, the fully connected layer. So these are the weights. What we want to do is we want to obtain these weights. And how to obtain these weights is you use this global average pooling and hence get the weights. What happens next is how does actually CAM create the heat map. It again takes the same channels that we took earlier. Instead of averaging it this time, it's going to use the class weights that it has. It's going to multiply this weight. So first cell into the weight, second cell into the weight, etc., to get a whole weighted gradient, weighted activation grid. It does it similarly for all the channels. Every channel would have one weight, and this is particularly class-wise because, as we saw, different classes have different weights. After it has the 3 weighted activation grids, it's now going to again do the same thing, weighted sample of each of the 3. So this and this is added, and then divide by 3. There are 3 channels to get this first particular value. Similarly, for all the grid cells, so this activation grid size is the same as what happens after the weighted sum. Now, if you can see, like this, ideally, this is a heat map, the color heat map that creates because of the normalization and the activation. But this is very small as compared to the image. So you upsample in this particular image and overlap it on the image. Whichever the darker areas are the ones corresponding to the prediction. Any issues in like the overall idea?
So essentially the filters are the things that actually contain the weights, the neurons, right? Those, when you have an input and you apply the filter, then you obtain a feature of them, right?
Yes. Yes.
And the channel is just that dimension of which filter are you considering?
Yeah, like one layer has multiple features, multiple
filters.
multiple filters, and one. So
Each channel is a filter, basically.
each channel is an output of filter. Channel is an activation.
Activation.
It's an output of an. So one image, multiple filters, one layer. One layer has multiple features. What happens is, for each filter is convolved with the image, you get one channel. Second feature, convolved with the image, you get second channel. Third filter, so every layer has multiple features, multiple filters. These multiple filters convolved with the input image gives you multiple channels. Each channel is an activation grid.
What's then the difference between channel and feature map?
It's same.
It's channels.
It's same, yeah.
And then you have n feature maps.
Yes.
Basically.
Yes.
And these gray things are denoting the channels or feature map, basically.
Yes. So like this whole is an activation grid. The darker things are basically just the higher values of the channel.
So things in the nth layer, these dimensions of the light gray ones are not necessarily the dimensions of the original image, right?
Yes.
Because this involving step, you have some right and so on. So is this what the upsampling is for?
Yes. 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 So what I'm going to get here is possibly a smaller filter size, like the filter convert, the activation size. But I need to, since it is a heat map, I need to superimpose it on the image to understand that which part of the image
so
it
this
corresponds.
basically relies on that the activations here are still spatially in the same region as in the original image.
Yes. Because due to this channels, this activations, this higher values, if you see this top center and this is high, so this part is quite darker. Because those are the higher values. That is the part where the higher values of the activations of the features actually. And since the CNN is supposed to learn the filters, like learn the features, and overall this final activation, like the final channel activation would have the whole concepts learned. These activations actually tell what concepts these are. And when you are superimposing them, you can find out on the image.
So the important information is basically that the features learned also encode the spatial information where in the image this actually it's not that just that the filter learns to detect edges, but it says okay here in this spatial location of the original image, this is what it is.
Yeah, that is how you identify edges, right? That the edges are the spatial location. When you are applying the filter, only the activations would be higher only where the edges are actually there.
So basically, if you have some certain pattern in some feature map, some deep layer, then you can derive that the original image in the same region there was.
Yes.
We're not using gap values here, right?
These weights are arrived from the gap values. We got the weights from the gap values.
By propagation during
training, yes.
And here in the next slide, so we just multiply, for example, 0.8 by each pixel, it would be right?
Each cell, yes, each of this. So 0.8 with this, with this, and they call the 16. So you are going to now get like a weighted. So now it would still be the same size, just multiplied by, like all the cells multiplied by 0.8. So another similar, this type of 16 4x4 map, but now multiplied with 0.8 at each cell. you get 3 of those here, and then you're just averaging those 3 together. So instead of directly averaging the 3 and using it, I'm going to use this weighted, I'm going to multiply this weights and use the 3.
But we weight them together in the end as well, right? So it's like weight, it's channel wise, right? So each channels get aggregated as well. Like in the right.
Okay, wait, let me. X1,
Mhm.
X2, X3. 0.15 into X1, 0.15 into X2, 0.15 into X3, and so on. This is for this one. Similarly, I will have for the above two. Then I'm just going to average it 1 by z. So this first cell, this first cell, and this first cell, these 3 values get averaged. These 3 values get averaged to get this first one.
Or it is divided by 3. I was doing it by these.
1 by z, number of channels.
These were the number of pixels in the slides, if I recall. They were not the number of channels.
Average 16 cells.
Yeah, all 16, that was Z.
No, but that is a gap formula. Okay, let me check that.
I understood it's per channel divided by 16 and then you add this.
Let me check that. Sorry. I always considered Z as 3. You're weighting each of them. Source of output. And like a.
The Z input pixels, spatial location.
Yeah. K is the number of, okay. K is the kth activation map. Okay, so it would be 16. I'm sorry.
We'll do it channel wise and then add those channels results together.
Yes. Yeah. Sorry. Divide by 16, yes. Sorry. Clear?
Essentially, if we had now fully connected layers between the or this gap, that we would basically, this would cause us to lose this spatial information, right? And then we cannot derive this heat map.
Yes, that is the limitation of CAM, that you need a CNN. Like this thing will only work on the CNN currently because it needs a gap layer. Like ideally CAM is for CNNs, but you need a gap layer which not every CNN has. You need to make sure there is only one output layer, one fully connected layer after the gap layer to get the weights. And hence this is all the architecture limitation with the CAM, and hence there is a grad CAM.
In the previous slide, so essentially the weight is the same per channel. If it's 0.8 applied to all 16. So ideally, the larger values are what get triggered in the heat map. And then we superimpose the 3 heat maps together in the end.
Yes.
With,
One heat map. This.
I mean, we have 3 heat maps.
Yeah, okay, yes,
we
yes.
superimpose the
You can,
channel
yeah.
into the image location.
Yeah.
So if it gets one location gets value from all the channels, it would be more red in a way.
Yeah, like you can see this is highlighted in 2, so
more darker.
more darker. Yes. And due to the limitation, now we have grad CAM. Similar to CAM, which has this one issue, we now have grad CAM, and this also happens during backward pass, but not during the training. No, it will be during the, wait, sorry. Now I'm confused.
Already has a backdrop.
It has already, like, basically during training, yes. So first forward pass, this runs in the backward pass. So here this was directly in the forward pass while training.
It has a back pass during training as well to calculate.
It has a back pass, yes, to get the weights, but the final weights that you get are like it's the same. Yeah, it's the same. So you have backward pass. So due to the limitations of the CAM that you cannot always have a gap layer, you necessarily need a extra linear layer, just one linear layer, and different other reasons that you always need a separate set for every single class, separate weight set for every classes that you have. There comes CAM. What CAM does is it uses weight, instead of using weights, reading the weights that already exist from the that we get from the CAM layer, it directly uses gradients that are already present inside the network. So what it does is we again have the same channels. The intuition here is that if a particular cell, if a particular cell is important to the final output, a particular activation is very important to the final output, the moment I'm going to change that activation, the output will also change. You get that at least the intuition? So what it does is it works on the sensitivity of the activations, and that sensitivity of the activations is basically what we call gradients, how much nudging something changes something. So what we do is take the feature map, nudge each of these cells slightly, and we check that how much y moves. One more thing, there are two y's here. Whenever xy comes together, it is the spatial location. Wherever this one y comes, it is the output y. And those are two different y's, just to make sure. So what it does is it's going to change one of the cell's activations a little, nudging it positive or negative, and calculate the gradient of that particular, calculate the gradient, how much y changes. So it's dy by df. So how much output changes when I'm changing this particular x and y value. And it will find out that, okay, for this particular cell, when I'm changing the gradients, when I'm nudging the cells, I'm finding which are the most sensitive activations that actually work for the outputs. And it does this for like every single cell and gets gets the gradients and then averages it to gets the weight instead of actually having the average pooling layer. So the main idea is, instead of using the gap layer to average the activation, you just see how sensitive are the activations to the output and directly use those activations, those sensitive activations, as weights.
So basically the left stuff is the filter and the right stuff is the result of the feature amendment.
Yeah, like the gradients of the activation, you will say that.
Yeah.
Yes.
So basically you would, for each of the filters, you would iterate over each neuron and individually not only this neuron up or down while fixing the others, right? So you basically have number of filters times number
Yes.
of
Yes.
stuff in each filter, many operates to where to do the
Yes.
backprop.
Yes.
But you only have to do the backprop up until this layer, not until like the first layer.
Yes.
So
You
have
don't.
to do full
Yeah, you don't.
backprop.
Yeah, you can just go completely back to this. So like even if you have multiple fully connected layers, just come back till the last convolutional layer and like the chain propagation.
So from what I understood, during forward pass, we nudge each, I would say, like the spatial location is what you're saying, like, or like neuron, what do we nudge?
This values, activation
Especially-
values. So
Okay.
after the filter is applied, we get the feature map. Every value of the feature
Is nudged.
nudged.
And then based on that, we get activation, I mean, new activation is what you're saying?
Yeah. Gradient of the activation, how it's
The
changing, how
gradient
sensitive it is. Yeah.
So the gradient changes with respect to the activation map.
Yes.
But the only thing that I don't get here is that when during training for both, we are kind of finding out the weights, right? So how is it different that way? Because in CAM we do find the gradients as well, and we do backprop. So backprop happens in both.
Yeah, but if you think of how normal back propagation happens, this happens by default in the normal back propagation. You are by default you are not doing an extra gap average pooling or any other extra step. You are by default getting these values when you are back propping it. due to the chain. So like from the output, I'm going to get this. So if I have the 4 outputs there, the final layer, if I'm going to start backpropping of this with respect to this with respect to the output, I'm going to get this. So there is no extra step involved. The normal backpropping does what we need.
But nudging has to be done by us internally as well, so we have to change the
That
activation.
nudging is based on the losses usually, right?
Oh, so we
Yeah.
go to the output and
Ha.
then we nudge based on, so the loss does the, so it's automatic in a way, the nudging.
Because like how do you actually backprop it? The loss, due to the loss, you are going to change something. Usually you directly change the input, like the backprop during a
Normally it's
normal.
with respect to the weights, but instead of it being with respect to weights, now it's with respect to the activation.
So when you are just going to go chain prop, you are by default getting this. You are not doing an extra step. You are just using what is actually already present. And you average all the values to get the weights. And just directly again multiply the weights with the channels. Since these are already gradients, you don't average it here. And just sum it and get the class heat map. And again, the same recipe, just upsample it to get the heat map.
What was the last one? What don't we do? Things.
Not averaging it, there is no 1/z. That's it. Because since I think these are already the gradient changes, you don't need that.
In the previous slide, that is kind of the gap layer itself, considering we are averaging it, we average 16 values in the next slide, and
Yeah, you're
you have to go forward. Yeah, here, average 16 values. So we still kind of, this is kind of the gap, kind of possible gap with backdrop in a way. Because we are still averaging the 16 values layer check.
possibly yes, but I think gap here does not just refer to averaging. It's I think also like gap is basically to find these weights. So like my idea, my understanding of this is that agreed that this is the gap, that the global average pooling that is happening, understandable, but the overhead that is at the overhead of the limitation that we actually have is that there has to be just one layer here. You cannot have more than one layers.
Which is frozen weights basically.
Yeah, but
from the normal process.
yeah, but here you can have that. Like my idea of gap is not just the global average, but like the whole part. Yes.
But here we learn the weights.
Yes, we are learning the weights by default by the back part.
And they're not frozen.
Yes. And again, it's the same multiplying the weights and getting the heat map. And I think even in the slides, that is how they are defining it. If you see, they are just directly doing the whole chain backprop to get the gradients, and essentially it is the same. I think for complete, you can just look at the gap paper and GradCamp paper and see exactly how it's happening. Usually you won't be asked the whole CAM or GradCamp explanation, but it's good to have the understanding. Even if you can see here, the blue arrows actually show the gradients and activations, that the activations are happening that way, but the guided back propagation actually changes things here. So yeah, and I think
from what I understood, the training is normal, so it's the same for both the cases.
the
But
back,
afterwards, after training, so the weights basically are not updated in a way.
yeah,
So what we learned during training is the guide in the forward pass, but during the backward pass, we take the gradient with respect to the activation. That's it.
yeah. So exactly no extra step, the normal. Like your, I won't, no, not the extra step, but okay, yeah. And like, yeah, that was it for fairness. Somehow I always take 2 hours. recording.